Hello everybody, welcome to another video on linear regression. So let's get right to it. We have here a data set, as you would say, an X and a Y. And very importantly, in Excel, you should always have your X on the left and your Y on the right. What does this data involve? Well, let's read. The data involves finding a quicker test for Alzheimer's disease. It usually takes a very long series of exams called the cognitive series. Researchers have developed the 7-minute exam, which is a quick and easy way to accomplish the same goal. So let's perform the regression analysis to see if the 7-minute exam does predict the same scores you would get in the cognitive series that is long and drawn out test. It'd be nice to know a quick 7-minute screen works just as accurately. But let's get into it. We have an X and we're trying to see if we could predict a Y from that. So what would I do? The first thing I would do right away is I would insert, I would do a recommended, and I'd look at my picture to really make sure it makes sense that I have, let me extend my picture a little bit here. So it really makes sense to have a linear regression. If I see a major bend, then maybe I would do a non-linear regression instead. It looks okay. It looks like I could draw a prediction line through there. And in fact, using the plus symbol on the trend line and then going to the arrow for more options, I can display the equation and the R squared to see what's going on. And so there's my prediction equation, which, yes, is down here a question. Prediction equation, the slope and the y-intercept, which I found. And I found the R squared. Notice I'm kind of answering some of these questions down below. What is the R squared? Well, that's 69.74%. All right. What is the slope? Well, the slope is 1.2959 according to my picture. What is my y-intercept? 7.9286. So I can read off the numbers really quickly. I can find the equation, which has the slope and the y-intercept, and the R squared really quickly utilizing Excel. The question, before I go any further into C, D, E, F, G, H, I really should check the assumptions of regression before I move on. You really should always check your assumptions before you move on and start hypothesis testing. So first, draw a scatter plot. We did that. Here's my scatter plot. And it allowed me to find some valuable information I will talk about later. Now, I'm going to back up and do my residual check. Because as you know, the residuals are the errors in the prediction line. And I want to make sure the residuals really add no value. Because if they add value, that means I'm missing something. So how does one do a residual check? You go to data, data analysis. Now, the reason I'm going faster is because A, you could pause the video, or B, you have looked at my previous videos that are more exhaustive in detail. So there's regression. Click OK. It's asking me for the Y. Okay, the cognitive is the Y. It's asking me for the X. The 7-minute screen is the X. You got to always determine your X and Y. I did not click labels. I do not care about the constant as 0. I will want the residuals, the plots, and the normal plots. These are the 3 things I request. You can have all the rest, but these are the 3 things I request for my checking. Output range? Sure. But make sure where you output it, make sure wherever you're putting it, below and to the right is empty. That's the usually safe bet. Below and to the right needs to be empty in order to see your analysis. And there we go. So now, utilizing this information, I can do a thoughtful, and in fact, you're going to want some space in here, a thoughtful assumption. So first, linear. Well, I checked the scatter plot. Is the scatter plot good enough for my information? Well, the scatter plot, the dots look pretty aligned with it. There's not much of a bend. Overall, everything's looking good in the scatter plot. You can also check out the residual plot. Is there any patterns in the residual plots by looking at the residual plot? You should blow that up a little bit. And I don't see any major bend, any major growth left to right. So overall, I think linearity is held in check. So this overall looks good. Independence. Well, if I was worried about time collection of this data, that somehow there was how I collected the data, and that means there's a relationship between the residuals, I'd worry about that. To me, there should be no reason to worry about how these tests were collected. These tests were collected from random representative people doing the survey, and it should not be based on time. So overall, this looks good. Though, if you're really worried about it, we have an advanced test, and you can look at my advanced features on the DW test. The Durbin-Watson test is a way to guarantee you, if you don't like just talking about independence, you're worried that really it's all about patient 3 scores. Does that interfere with patient's 4 scores? Patient's 4 scores, does that interfere with patient's 5 scores? Is there some relationship from previous scores to post scores? I don't believe there would be in this type of scenario. But if you're worried about it, you can run the Durbin-Watson just to check it. All right, we have normality now. Of course, we're going to be utilizing the test later, the t-test for slope. To utilize that, you got to make sure normality is in the residuals. So we can look at the normality plot of the residuals, and what you're hoping for is a roughly straight line. See, what the normality plot is doing is plotting your residuals against where they should be respectively against the normal plot. It's kind of a one-to-one plot. And as you see here, for overall, my data looks roughly normally scattered. And I'm happy with that. The NPP plot looks like a straight line. If it didn't, I would be wondering if you chose the right picture. Of course, it should have came out here, but maybe you missed it. Maybe you missed it, and so the normal plot, there was a bend. If there's a bend, most likely you're dealing with some outliers or you're dealing with the wrong graph. If there's a massive bend on one side or the other, you're probably looking at some type of transformation you should utilize because your scatter was not linear that you thought it was. It's a way to check to make sure your scatter is linear. And the normal plot does look roughly linear, so normality is achieved. Equal variance, it's all about the growth in the residual plot. In my residual plot, as I look left to right, is there any growth or decay of the data? That is there an explosion of the spread? That's really what it is. It looks like right now the spread is roughly the same across as I go left to right. As I go left to right, there's not an explosion or a decay in the spread, which tells me overall there is equal variance. And I need equal variance because this is how I build an accurate confidence interval. Look at part F. I want to build a confidence interval for the slope. I can't trust my confidence interval if I don't trust my spread. And so I see no growth / decay in the residual plot. And so I'm happy again. So overall, my checks look happy. All right. So I'm happy with my prediction equation that you see here. So let's dive deeper now that I'm happy with my checks. What does the prediction equation slope actually mean? Well, think about the question. The question is all about predicting scores, right? In this respect, we're looking at a 1.2 differential between one test to the other test. And you got to understand what it means. It means a 1 point increase in the 7-minute test means a 1.22 point increase in the cognitive test. That's what it means. It means if we change the x, all right, if we change the x, which in this case the x is, just remember, the x is the 7-minute screen. So we change the x by 1 unit. So a 1 unit increase in the x, the 7-minute test, means on average we should see a 1.22 point increase in the cognitive series. That's what it means. What does the y-intercept mean? Well, the y-intercept is when x is 0. So what it means is if we get a 0 on the 7-minute test, we expect a 7.92 on the cognitive test. I really never put much stock into the y-intercept unless we have scores close. But since my scores are pretty far away from 0, I don't have values down there. I don't like to predict too far away from my data set. I'm very happy predicting between my 2 blue points on the X values. So between like 3 and 14, I'm okay predicting. You can predict lower and predict higher, but understand your regression, that is your prediction regression, is more valid between the points you have. So I'm happy predicting for 11, for 12, for 13, because I have dots to substantiate my claim. Yes, people do predict lower than higher, but you just got to be careful and understand that. And if you get too far away, you don't know if this graph makes a major bend, a major turn, and linearity may not be fully vetted there. My checks are only based on the residuals, the errors in my dots, and my errors are based on the range of the x's. So you got to be careful of that. I always mention that when people ask me what the y-intercept does, and it is a base score. It's a base score if x is 0. But unless you have data close to that base score, if we had some points lower here, then I wouldn't put much stock in that y-intercept. I can define it, but I don't have much stock in it. I do have a lot of faith in the slope because I believe in my prediction line. All right, let's move on. What's the r squared? Well, the r squared, this is very important to me. This is the percent of variation in the y, the percent of variation in the y, in this case, the cognitive test that can be based on the 7-minute test. What it means is the fluctuations I'm seeing in the scores in the cognitive test, a huge amount of that variation can be predicted from the variation in the 7-minute test. So 69% of the reason the variation in the cognitive test will vary can be based on the variations in the 7-minute test. So there is a nice relationship between the cognitive test and the 7-minute test. There is a lot of nice, powerful statement stating between the 7-minute test and the cognitive test. Let's keep going on. Can I make a prediction? Sure, I can make a prediction. Tell me what you want me to predict for. Oh, somebody took the 7-minute test and got a 10-point score on the 7-minute? No problem. If you know what they got on the 7-minute score, the prediction equation, the purpose of the prediction equation is to make a prediction. And so I would say there's my slope. I'm going to multiply it by 10 because that's the 10-point score. And I'm going to enhance it by the y-intercept to get your cognitive test score. And there is your cognitive test score. A 10-point score on the 7-minute screen probably means they're going to get a 20.1876 on the full-blown cognitive test score. I mean, the purpose of the prediction line is to make predictions. So if somebody comes in with a 10-minute test, they take the 7-minute test and they get a 10-point score, I'm predicting they're going to get a 20-point on the Alzheimer cognitive series. It's all about, do you trust this test? And because of my background check here, I trust the test. And because the r squared, I really trust the test. I got some really good positive momentum saying this is a really good, strong prediction. Let's continue on. Now, of course, that slope is based on just a few samples. So somebody could ask, all right, so that is based on a sample. What if you know that you're off a little bit and you like to move the test scores up? That is, could you move the test scores up? That is, could you change the slope a little bit and be okay with it? The answer is, of course. The 95% confidence interval for the slope, what it looks at is and says, this is your sample slope. It says that's your sample. What I could do is build you a slope based on that sample slope. Let me go to the home menu so I can highlight it. And I can look at potential lower bounds and upper bounds on the true confidence interval slope. So I believe that's this question right here. Yep. And so what I have is a 0.53 to a 2.06 window where the true slope, if I studied every single patient, I have a 95% confidence, and that's what it is. There's a 95% confidence that the population slope, that is, if I took every single person that came in and wanted the Alzheimer's diagnostic test, I know their score, so 95% confident that the true slope is between 0.53 and 2.06. That's the bounds on the slope. The sample slope is 1.22. That's the sample slope. And by the way, the sample slope is snugly between these two numbers. But if you wondered, how low could I go with this sample slope and still be confident in my prediction? The answer would be 0.53. How high could I go on my sample slope and be confident with my prediction? 2.06. So for some reason, you wanted to change your prediction equation and change the slope to a lower number. You could change that slope to a 0.53 and then repredict. Or on the other end, if for some reason you wanted to change the slope to a higher end, you could change it to a 206 and then repredict, which would obviously change these prediction outputs. I'm using this slope as my predictor, 1.22. But if you want to change your predictions to a lower and to a higher end, you could. And that's what the confidence interval will allow you to do. See, again, your prediction equation is based on your sample slope, not your population. All right? You're basing your prediction on your sample. You just hope your sample is good, and that's why the checks are important. But if for some reason you wanted to lower or to increase the prediction, you could do so utilizing this 95% confidence interval for the slope. What I use it for is for this deeper question down farther. That is part F. Looking at the confidence interval, what does it tell me about a significant relationship? Well, what it tells me is 0 is not in the 95% CI. So I believe I have a significant linear relationship. Why is that? The answer is because if 0 is in the interval, that means the slope could potentially be 0. And if 0 is a potential slope, okay, if 0 is potential slope for the true population, that means my prediction line could be horizontal. And if my prediction line is horizontal, that means you really don't have a significant prediction ability. We look at this confidence interval, and if 0 is between these two numbers, there's a potential you don't really have much of a relationship between X and Y. The good news here, 0 is not in this interval. The lowest the slope gets is 0.53. That's not lower than 0, which means, according to my confidence interval, I have a significant linear relationship. Awesome. You could also do a t-test for the slope. Sure, you could do a t-test for the slope, and the t-test and the corresponding p-values are right there. That's the thing. Excel has everything preloaded. The t-test is right there. It's a 4.01 t-test, or 02 t-test if you're rounding. The p-value is 0.005. And if you remember anything from hypothesis test, if your p-value is extremely small, like this one is, all right, this is less than any alpha I care about. Remember, alphas are typically 1%, 5%, and 10%. Your p-value is clearly under 1%, 5%, and 10%. So this tells me I reject H naught since my p-value is so small. And this means, well, look at your H naught. Your H naught is your population slope is 0. That's what this test is for, by the way. The t-test for slope is the test for, are you sure 0 could not be a potential population slope? Are you sure? Well, let's test it. I'll assume maybe it is 0. And if my p-value comes out small enough, I'll say, nope. And that's what this means. And this means the true, can't spell, true slope is not 0. And what does that mean? Well, it means by the hypothesis test, by the slope HT, we have a significant linear relationship. You see, if 0 is in the interval, or if 0 is potentially a possible slope, and that means you would not have rejected in the hypothesis test, then there's a potential that you don't have a strong linear relationship. But because my hypothesis test and I reject it, this tells me I don't believe in H0, which means I believe the slope is not 0. If the slope is not 0, that means it's either positive or negative, and that means we do have a significant relationship between the x and y values. Vice versa, same thing here. The confidence interval backs up my t-test. My confidence interval should always back up my t-test. My confidence interval does not contain 0, and that means, once again, we have a true significant linear relationship. So not only do the checks verify that I have a significant linear relationship, not only does my R-squared check it, but the t-test for the slope and the confidence interval for the slope verify it. This is also, when I make a prediction, I believe in my prediction. That's what it really comes down to. I want to make a forecast, and I can because of all the checks I have done, whether it be the regression checks, whether it be the t-test for slope check, whether it be the confidence interval check. I now believe in my prediction line, and if you believe in your prediction line, you better know what the slope and y-intercept mean so you can tell the person what the slope and intercept mean when you're predicting. Now that we've done all this analysis, now we have something significant here, don't we? We now know we have a quick, fast, easy test for Alzheimer's. A nice 7-minute test, and it is pretty accurate. You can look at the R value, by the way, right there if you're curious what the R value was. There's the correlation number right there in front of us. The correlation number was 0.835 if you cared. See, all the information is at our disposal. We just got to understand what it means in the end. And in the end, we have a very significant prediction equation. So what it tells me is the 7-minute test is doing a really good job of examining the Alzheimer's patients, or predicted or potential Alzheimer's patients. And so after the 7-minute test, you know what I'd do? I'd make them go through the cognitive test if needed. For those people on the 7-minute test that don't score high enough, I'd say, nope, no need to put them through the heavy-duty cognitive test. And that's what we've done here, is we've now given the people that come in and go, you know, I might have Alzheimer's, or I might think I have Alzheimer's based on blah, 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 blah. Well, we can give them the 7-minute test and not put them through the stress of these long, cumbersome cognitive series tests. And that's what we want to do. We want to take patient care to the next level. And we could do that just by utilizing what I've got here in front of us, a clear test. All right, guys, thank you for watching this video. Stay tuned for others.